All right, 6.2 notes. First of all, if it would really be beneficial for you, especially with this year with open notes and people aren't doing enough practice problems, to do this problem by yourself without seeing the answer. So I have it covered up. I'm going to just move it in a second. You could, of course, you should pause it now, and you should try doing this problem by yourself. So pause it and do the problem by yourself. And I'm going to wait for you. Ready? Okay, I waited for you. Long time. So now here we go. Now we'll talk through it. So calculate and interpret the mean and standard deviation. So again, here's it actually written out. This is the way you can abbreviate it. So mu of x equals the expected value of x, item 1 times its probability, item 2 times its probability plus ... Calculate. The College Board lets us do that. 2 to establish the pattern. Same thing for standard deviation. And again, if you're like, oh, then I don't have to worry about this because I don't have to you have to write out 2 steps correctly. Okay, now remember, we got the average here. First thing minus the average squared times its probability. Second thing minus average squared times its probability, and so on. And again, we get these numbers right from the calculator. We had that a couple times last time. I really wasn't planning on spending time plugging that in the calculator. All right, then the interpretations. Again, hopefully you'll stop doing the deal where you don't do the interpretation. You just do this part and stop. Eventually you have to stop. Some of you have to stop doing that and get them right the first time. If we select many El Dorado Country Club community college students, we'd expect the average number of units to be about 14.65. And they have units instead of credits for whatever reason, because they're special. And then we get the standard deviation. If we were to randomly select A, now that's something maybe we didn't talk about last time. When you do the interpreting the mean, you're doing a large count. If I do this a whole ton of times, I will get this number on average. Standard deviation says if I grab a student and I look at them, I expect to be typically off by this far away from the mean. So if I randomly select a student from the El Dorado Community College, then the number of units will typically be off 2.056 units from the mean. Probably having the word units there probably is a little repetitive, but there you go. All right, so again, mean, I do something a whole bunch, this is what happens. Standard deviation, typically when I grab 1, it's this far away from this number. All right, the next one says, all right, well, let's change things around a bit. So let's go back to unit 2. Remember that multiplying changes both the standard deviation and the mean, but center and the spread. Adding only changes the center, not the spread. Okay, so this one says, all right, so we charge $50 per unit. That's probably a little outdated. I bet you it's more than that. Even for a community college, that seems ridiculously cheap. So then what happens? Well, the standard deviation is now these values, but I want to point out, don't forget what we could have done is we could have taken this average, 14.65 times 50, and we get this number right here, right? Because if we multiply a number of take a multiplier times every piece of data in our table, it will multiply the mean. It will also multiply the standard deviation by 50. So this is almost 2. 2 times 50 is 100, and it's a little bit more. Again, you still have to show your work. And you're like, oh, that's too bad. Just show your work. Them's the rules. Not my rule, their rule. Okay, and again, I kind of jumped the gun, which I typically do, right? So if the center is multiplied by 50, the spread is multiplied by 50, they didn't ask, but I just include this. The shape always stays the same, no matter what happens with these. All right, so we had the units, then we multiplied by 50 to get the dollar amount, okay? And then now what happens? Well, now they say, oh, by the way, so not in addition to $50 per unit, it's $100 for fees. I thought maybe it was a. No, they don't say. They just say fees. So whatever. We'll just maybe a computer fee or a lab fee or whatever. So the mu of x again, now this time we're not using we're not actually calculating based off the table. We're just using the values. And we could have done that for this one as well. But I wanted to make, this one we're talking about the shortcut. In a regular year, you know, we would be in groups and I'd be having you all write that out. But there you go. That's what's going on there. So this one, again, we would add 100 for the center, but sigma doesn't change. It stays the same. Just adding all the values does not change the spread. So what happens when you add? The spread stays the same, the shape stays the same, the center changes by whatever you add or subtract on. All right, and then here this is like if you're a formula person and you must have it in a formula. Let's see, we have a couple here with the formulas in there. But this, again, when you multiply or add into an equation that has an x and a y, so that you have a linear, and then you change it, it's like linear transformations. That's kind of what they got, right? They're linear transformation. So what happens, again, you say, okay, so what does all this mean? For sigma, all you do is if there's a multiplier, okay, this is the, what happened, this is a multiplier, the multiplying affects sigma, okay? Multiplying affects mu, and adding or subtracting affects mu as well. All right, so there you go. So next example, in a large introductory statistics class, the distribution says x equals the raw scores on the test, approximately normal with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw by 4 and adding 10. Multiplying by 4 and adding by 10. So we have x was the raw score, now we have y as the scale scored. And we have this is our linear transformation. Added by 10, multiplied by 4. All right, so mu of y, and again, this is trying to force this into this equation instead of just doing what we did with the El Dorado Community College problem. But for here, for the mu, the 10, adding of 10 and the multiplying of 4 from the raw score changes to the scale score. The standard deviation does not have the plus 10, just the times 4. All right, so then this is now mu of y and sigma y. So now we can use, since we have normally distributed, and we can say what is the probability that a randomly selected student has a scale score of at least 90. So y follows normal distribution with mu of 78.8 and sigma of 15.2. State the distribution. We already have defined the y here. The probability that y is greater than or equal to 90, normal CDF. Put in all the information and I get that value and then answer the question it sends. About 23.06% of students will score at least 90 on the scaled score. All right. So those might call that linear transformation problems, but we'll see that in many different ways. Adding does not affect standard deviation. That's really the only thing you need to remember. Everything else just makes good logical sense. All right, here we go. Suppose that the height m of a male speed dater follows a normal distribution with the mean standard deviation given. Females are also normal with a different mean and standard deviation. What is the probability that a randomly selected male is taller than a randomly selected female? This is a big problem, but this is one we're going to definitely have to get used to, and it has some little funky down here and standard deviation down here. We'll get to that in a minute. So anyway, I've defined my variables. So the m is the height of a randomly selected male speed dater, and then f is the female, and then I'm going to define d for difference, but we're just going to define d as males minus females. And here, this is not part of the definition, but just for notes, if it's positive, then the male is taller. If negative, female is taller. And sometimes we don't think about this very carefully, and it can be a problem. All right, the average of the difference is the difference of the averages. The average of the difference is the difference of the averages. And just be happy that it works out that nice. So on average, the difference is 4.5. positive, so 4 point, the average. If I randomly take 2, and I do that a whole bunch of times, my male is going to be taller than the females by about 4.5 inches on average, if I do a large number of them. All right, now here's what gets weird. For sigma, we have to, remember, we cannot add or subtract standard deviations. We can only add or subtract the variances, but we never subtract variances. Now, for now, you're just going to have to take that, and we'll talk about that more later. So if you're like, oh, well, you never subtract variances, you only add them. Why? Because Mr. Hughes said so, or Mr. White said so, or whatever. For right now, that's just going to have to be good enough. All right, so then what we do on this problem to get the new standard deviation is we would take the sigma, the standard deviation squared for males. We would add the standard deviation for the females, and we would get 4 squared plus 3 squared. It kind of looks like a squared plus b squared equals c squared with the Pythagorean triple right there. All right, sorry, forgot something here. So the standard deviation of d would be equal to 5. So again, we add the variances and square root to get the standard deviation of the differences. Sigma d is equal to 5. Really, I guess probably like just right here, kind of had to just box that. In fact, I'm going to change that and put that. And this is in inches. Let's go ahead and get that all in there as well. All right, so what's the probability that a randomly selected male is taller? That means the difference has to be greater than 0. Now, equal to 0 would be the same answer, but it says taller, not at least as tall. Taller. So we gotta be careful. Gotta use some of that algebra 1 stuff in there. And then from 0 to 1,000, because and 4.5 to 5, 0.8179, answer the question in context. About 81.5% of the time, a randomly selected a male speed dater will be taller than a randomly selected female speed dater. Now it says it. All right, one more page here for 6.2. Here we go. This one is a common problem, and I can also already warn you this one is on the tests. Suppose that a certain variety of apple weighs or approximately normally distributed with 9 ounces with a standard deviation of 1.5. Bags of apples are filled with 12 apples. What is the probability that the sum of the 12 apples is less than 100? Okay, so again, what we're going to see here is we say, well, here's what's going on with 1. But now we're gonna box them up, not in singletons, but in a box of so many. And we don't get really creative with these. It's going to be a box of something else when you see the test. But X is the weight of a randomly selected apple, and I did T for total. T is the total weight of 12 apples. Define both variables. Remember, I started talking about variables in this unit. It's not because things were going to get less complicated. You need to define this stuff. Okay. Then mu of x and sigma x was given, but I go ahead and I write that. Mu of t, now remember with the averages, it's easy. If the average is 9 ounces and we do 12 of them, the average of 12 is going to be 108. Okay, so mu good, sigma no. Okay, and to do this one, you would have to do 1.5 squared plus 1.5 squared 12 times. Okay, now what we're going to want to get used to doing is writing it this way. Okay, it's really 1.5 squared plus 1.5 squared plus 1.5 squared. Before the corner bets, there was only 2 things. Now there's 12. So you can either write it like this with the dot, 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 or you're going to want to calculate it this way. It's much easier. So you do the same thing and you add them up 12 times. It's the same thing as doing it once, multiplying it by 12. Square root, there's our answer. Okay, so there's the mean and the standard deviation of 12 apples given the mean and standard deviation of the 1 apple. I'm sorry, right here, lost my place. What is the probability that it'll be less than 100? Okay, so then it's state, do, conclude. State the distribution. Okay, we already defined the variables up here. And then we kind of had to calculate what the number that this new mu and sigma is going to be. I can't use this number here with the 12 total. So what is the probability that the total is less than 100, not less than or equal to normal CDF? I chose 0. I figured we probably don't have to worry about negative weights of apples, and typed in the rest of the information. Not too likely. Okay, the average is 108. Standard deviation is that's over a standard deviation to the left of the mean. Probability that a randomly selected bag of 12 apples is less than 100 is about 6.2%. State, do, to conclude. Well, maybe I should say define, state, do, conclude. Don't forget to show your work. Don't forget your probability statement. You'll be very irritated if you get points taken off for forgetting that. But that's right there, that's a really strong problem. And then a lot of times they might say something like, oh, well, then we put the apples in a box. But we'll have to check. We'll have to save that for another day of stats fun. All right, and then we have these check for understanding. By the way, these check for understanding come right out of the textbook. I know a lot of you aren't looking at the textbook, but some of these were so good that we put them in the notes. So again, this would be maybe even a warm-up for the next day, or this would be an opportunity for me to make you all do another problem in groups. But I'll just talk through them like normal. You can always pause it here, try to type this in your calculator, and get the answers. All right, so this one, they're talking about the cars sold versus cars leased. Okay, so they're going to be doing the difference again. All right, so they said define D as X minus Y, and again, normally like difference or total, because they want to, well, anyway, assume that they're independent, find and interpret mu of D. So mu of D is X, or mu of X minus mu of Y, 0.4. Remember, mean is easy. The difference of the mean is the mean of the difference, and vice versa. It couldn't be any nicer. If we find the difference of many, many pairs of randomly selected days, now that one, the context gets a little bit trickier because we're trying to find, anyway, we'd expect the average difference to be about 0.4 cars of the difference in the sales versus the leases. Sales versus leases, 0.4 means more sales than leases. All right, what about standard deviation? Okay, well, remember, so, and they gave us this, I'm getting these right from here. You can't add the standard deviations. You add the variances and then convert it back into standard deviation. And again, that's there's no way of getting where you have to be able to do that. You don't know how to do that on the AP exam, you will miss FRQ question and a multiple choice question guaranteed. Okay, the next one says they receive a bonus of $500 for each car and $500 for each sold, $300 for each lease. Find the mean and standard deviation of the difference of the manager's bonus for the cars sold and leased. All right, so this one is definitely a little bit harder. But anyway, so sorry, we take the mean of 1.1 cars sold. We take it times 500, so we say, well, that's on average $550 worth of sales bonus. We sell on average lease 0.7 cars, $300 of bonus. Average $210 bonus for the average bonuses for the lease. All right, and then right here, so then mu of the difference is just the difference of the mu's from before. And then for the standard deviation, again, we're taking the 500 times the 0.943, and then to get the standard deviation of the lease, 300 times 0.64. That's how we get those numbers. And then for the standard deviation, again, even though I know it's difference, we have to add the variances. And so that's first of all, you can never add standard deviations or subtract them. You must convert them into variances by squaring them and then add them and then convert it back to standard deviation. And on top of that, you never subtract. Always add. Always add. All right. That is 6.2 notes.